You've been told that most matrices can be inverted. That's a lie, or at least half the truth. Here's a non-square rank-deficient matrix stamped with the words, "Inverse does not exist." And yet every matrix, with no exceptions, has a perfect inverse. You just need to know where to look. This is the pseudo-inverse, a perfect map between row space and the column space. The secret lives inside the 4 fundamental subspaces. To find this hidden inverse, we need to know exactly where a matrix lives. Take any matrix A with m rows, n columns, and rank R. The rank counts the number of independent rows or columns. That single number R controls everything. 2 of these subspaces share the dimension R, and that shared dimension is where the magic happens. The 4 fundamental subspaces. Inside the input space, R to the n, live 2 subspaces, the row space and the null space. The row space has dimension R, the null space has dimension n minus R, and it holds every vector that A sends to 0. Notice that R plus the quantity n minus R gives back n, so together they fill the input space. Now turn to the output space, R to the n. Here left the column space and the left null space. The column space has dimension R matching the row space exactly. The left null space has dimension m minus R, and again R plus m minus R gives back m. The row space and the column space, both of dimension R, are the 2 stars of this story. The matrix A maps the row space perfectly onto the column space. A clean one-to-one correspondence we will call the perfect map. Null spaces are the villains of this story. When R is less than m and R is less than n, both null spaces are non-zero. Remember from before, the null space has dimension n minus R, and the left null space has dimension m minus R. So whenever R falls short of n or short of m, those dimensions are strictly positive. And the null spaces contain more than just the 0 vector. A null space is a set of vectors crushed to 0. Once a vector becomes 0, you can't recover where it came from. Many different inputs all collapse to a single point, and no reverse arrow can untangle them afterward. This is the precise reason an ordinary inverse fails. The information has been destroyed. Here's the central claim. Take any vector s in the row space, then A times s lands in the column space. Restrict A to the row space alone, and this mapping becomes a perfect bijection between 2 R-dimensional spaces, 1-to-1. Distinct row space vectors go to distinct column space vectors. Onto every column space vector gets hit. Inside these 2 special subspaces, A behaves like an ordinary invertible matrix. The pseudo-inverse, written a plus, reverses exactly this map. I claimed it's perfect. Let me prove it, starting with 1-to-1. Suppose vector x and the vector y both live in the row space, and A times x equals A times y. Let's subtract one side from the other. A times x minus A times y equals 0. So by factoring, A times the quantity x minus y equals 0. That tells us something important. The vector x minus y lives in the null space of A. But remember, x and y are both in the row space, and the subspaces are closed under subtraction. So x minus y must also live in the row space. Now here's the key fact. The row space and the null space are orthogonal complements. They are perpendicular to each other. The only vector that can sit in both at once is the 0 vector. Therefore, x minus y equals 0, which means x equals y. The map is 1-to-1. Proven. Let's make this concrete. Take A equal to the 2-by-2 matrix whose 4 entries are all 1. Its rank is 1 because the 2 rows are identical. The row space is the line spanned by the vector 1, 1. The null space is the line spanned by the vector 1, minus 1. These 2 directions are perpendicular. Their dot product is 1 times 1 plus 1 times minus 1, which equals 0. Since the 2 lines are perpendicular, the only vector lying on both of them is the origin. So restricted to the row space line, A is perfectly reversible, 1-to-1, even though A itself flattens the entire plane down onto a single line. Now let's define the pseudo-inverse precisely. The pseudo-inverse, written A+, takes any vector in the column space and returns the unique row space vector that maps to it. It is the literal inverse of that bijection, the one-to-one correspondence between the row space and the column space. And critically, A+ sends the left null space to 0. It wipes out exactly what cannot be recovered. This is the mathematically honest answer to the question, how do we undo this matrix? It gives a true inverse where inversion is possible and a clean discard of the rest. Here's a common mistake, believing that A plus times A equals the identity. In general, it does not. To see why, take any vector in Rn and split it into two pieces, a row space component plus a null space component. When you apply A plus times A, it keeps only the row space part and throws away the null space part. That's exactly a projection onto the row space, not the identity. Likewise, A times A plus is the projection onto the column space. You only get the true identity when the null space is trivial, meaning the matrix has full column rank. Otherwise, this projection is the closest any inverse can possibly come. This isn't just elegant geometry, it's why regression keeps working when it has every right to fail. Ordinary least squares estimates coefficients with the formula x hat equals the quantity A transpose A inverse times A transpose times B. That formula requires full column rank. Now suppose two of your predictors are perfectly collinear. For example, a feature recorded in two different units. So one column is just a scalar multiple of another. Take A with rows 1, 2, 2, 4, 3, 6. The second column is exactly 2 times the first, so the columns are linearly dependent. As a result, A transpose A becomes singular. Computing it gives the matrix 14, 28, 28, 56, and its determinant is 14 times 56 minus 28 squared, which is 784 minus 784, equal to 0. With a 0 determinant, the inverse is undefined, and the whole formula collapses. This is where the pseudo-inverse steps in. X hat equals A plus times B, delivering the minimum norm solution gracefully, even when the ordinary inverse does not exist. The big idea: every matrix has a pseudo-inverse, no exceptions. It acts as a true inverse on the part of space where inversion is actually possible, providing the perfect map from the row space to the column space. And it gracefully discards the null spaces, the directions where information is lost. Non-invertible matrices aren't broken. They simply reserve their inverse for the subspace where reversal genuinely makes sense. That hidden bijection is always there, and the pseudo-inverse is the key that unlocks it.